Thank you very much. I'm very happy to be here, and thank you for the invitation to speak at the number theory seminar. It was a bit of a short notice, but I will do my best to. So I hope the timing will be all right. So I will speak on our work in progress with Calegari and Tang, which is a sequel to a topic that was reported last year in the number theory seminar. This was the distribution of the unbounded denominators conjecture in non-congruence modular forms. And I would like to show what else the ideas in the proof can be used for. I'll start with a basic question in most elementary terms. So I will actually get to explain, the precise meaning, but G function, that will mean there is a linear differential equation with polynomial coefficients, and we suppose that the singularities are only at 0, 1, and infinity, so that we have that means now this branch, this power series is obviously regular at 0, but the minimal differential operator annihilating function can have singularities at these points. And so my question is,
the denominator is the GCD.
Yes, I should start with that. So this is the standard notation for the GCD of the first 10 integers.
That's here.
Like, okay. So this, we have an integrality type. Sigma is some positive or non-negative integers. And we consider those power series which have the form some integers an. These are the allowed denominators for the truncations up to, so it means that up to the x to the n truncation, we put the GCD of all the n coefficients, and they can have this form. So obviously they grow geometrically by the prime number theorem. So this is what we call example of a G series. And okay, the question is, what are the examples which have, so this question means when we put these singularities with normalizing this way against this precise integrality type. And there are obvious examples. So let me start by saying this is a question that I do not know how to answer in general, but we will give some structure, some results for small values of sigma. And so there are the polylogarithms, or more generally, we take any polynomial in the polylogarithm series. They obviously have this type and those singularities. So it could be maybe, so my question is, are there other functions? So one thing that is easy to see for the start, so I have chosen a hybrid presentation mode to show some visual pictures later on. So I apologize if that is inconvenient, but let me start with this example. If we have actually integer coefficients, so that means just power series z of x, this question is very easy. So having singularities only at 0, 1, infinity. Well, by the Poyat-Carlson dichotomy, such a function can only be a rational function, because the dichotomy says that either there is a natural boundary on the unit circle, or, okay, then if it extends just a little bit past some point of the circle, that means the function is analytic on some domain G in the plane with conformal or Riemann mapping radius strictly greater than 1. And the rationality theorems, starting with Carlson, Poyat, Begrandius, and this sequence of arithmetic algebraization nature, we have that the function is rational. And so the question acquires a meaning when, so firstly, sigma is positive, and it is important how we normalize the three singularities. And to contrast, if we had in the previous discussion that Tang presented at the number theory seminar for the unbounded denominators conjecture, we were concerned with integer formal functions. In fact, for the most part, these were algebraic functions of the modular lambda function. But then we have a different normalization. The singularities were at 0, 1 over 16, and infinity. And then, okay, so it's a different problem. So I want to let me describe how this form of functions occurs from modular forms, so how it is related to the subject of the previous work, and how can we use the techniques. So I display a classical identity taken at random from Fluke Klein, where we have a modular form. Here it's a higher weight. Let us, maybe that is, maybe I'll consider the fourth root of both sides, but this is more precise. So we take a classical congruence modular form. It has an integer Q expansion. And now, obviously, it's not a function of this form. It means that it is not holonomic. It is not, does not satisfy linear differential equation if we write it like a Q series. But if we write it in terms of a half module, say 1 over j in this case, or the modular lambda function in our previous paper, then it is.
So this is to be interpreted as an identity of Q expansions.
Yes, that's right.
Because the right-hand side j is a modular function, on the left-hand side you have a modular form. So you just mean you take Q expansions and it holds.
Or it means that you take 1 over j, right, and then you substitute formally by. So we have j, any power series in that I can write as a Q expansion, let's say, and that's the meaning of this identity for us. But this is in this coordinate, the function is holonomic. So I want to connect to the previous discussion that some aspect of our theorem which was not discussed then, so there is generalization to vector valued modular forms, and the definition is okay. So here we can restrict to the full modular group without loss of generality, because we can always induce from a finite index subgroup by raising the dimension n of this VVMF vector valued modular form. And by definition, this is a holomorphic mapping. That means a pair of holomorphic functions on the upper half plane. Then there is a representation of the modular group, which is at least in weight 0 is like a monodromic representation. Think of restricting to the subgroup gamma of 2, which has no elliptic points. And then for k equals 0, this next definition just becomes the same as a local system on essentially on y of 2, which is p1 minus 3 points. And then the next definition is what we find in the literature, and what makes our proof work is a special assumption to that this matrix is semi-simple, and then there is the growth condition of the cusp. Let me not spell out except say that the last two conditions together mean that there is a Q expansion, roughly speaking, a Fourier series in general with complex coefficients beta I in this generality, but no log Q terms because of that semi-simplicity condition. And then the theorem, okay, so if we have, let's say, S-integer coefficients, then certainly these exponents are also rational. So we actually have Puiseux expansions. And that, and then I want to contrast this with what I believe is called the logarithmic vector valued modular form in the literature. The same definitions, but without any condition on this matrix. So here, the expansion, asymptotic expansion at the cusp, they have log Q terms, or powers of log Q. And just to connect, I state a very special case of this conjecture for with replacing vanishing of almost all picovectors by just saying that almost all of them are integers. So this means that we have all components of the vector valued modular form belonging to some finitely generated heap. And then one expects that this is equivalent to having the kernel finite index subgroup. So it's the algebraicity conjecture. Instead, well, we cannot answer that. We can, but if we replace S integer by just plain integer, the following are equivalent. All components have integer Puiseux Fourier expansions. Is equivalent to rho has a finite image, the algebraicity part, and the congruence kernel. And it turned out that this part of the conjecture, the more classical, case that was explained in last year's number theory seminar, is the bulk of the proof. The latter part is very much.
Probably you shouldn't assume everybody was at the talk last night.
Yes, I was. So that is also why I wanted to connect to the topic by revising it in a slightly different form with these vector valued modular forms. So let me just make less allusions to that last year's seminar. Some just, but it will be a self-contained talk. What are examples of logarithmic vector valued modular forms with integer coefficients? And actually already here I have some questions that let's say some generalization of the conjecture which we cannot answer with our method. So the lambda function is this quotient. So I use this notation of the theta series, and with these normalizations, it has the expression as the essentially quotient of two theta series of the fourth powers, and there's the product with identity with the dedicated data function. So this had coefficient. This is divisible by 16 in the ring of integer q series, and that is where we have the singularity 1/16 in the normalization. So the first identity, I hope I'm not. Okay, I think that should be due to Jacobi. It is that we take the hypergeometric function power series with parameters 1/2, 1/2, and 1. Then we plug in q back the lambda of q, and the result is a modular form, the square of the theta series, which is of weight 1 for gamma of 2. So this is what we do call theta squared. This is an instance of the principle of this. We started. Conversely, we could start with this modular form and then write it in terms of this half module, lambda over 16. So the point was that we have identity of now formal power series with integer coefficients. So this is exactly equal to z of q. And then we get holonomic function. So this satisfies, in this case, Gauss's hypergeometric equation or Legendre's equation. This one, and that is essentially the first, the elliptic integral of the first kind that's denoted by k, I believe. And if we take the other one of the complete elliptic integral of the second type that's denoted by e, so it means we change the parameters to 1/2 minus 1/2 of 1. Well, obviously, in this case, we also get a vector valued modular form, but now it's logarithmic with integer q expansion. So this falls outside of our result. And indeed, so obviously it has integer q expansion. It has some kind of formula with theta functions and the Ramanujan, I think, theta operator. It involves E2, which is only a quasi-modular form. So the question, our method does not apply to this situation at all. And furthermore, so my question is on the next slide. First examples. Observe that, so this series is essentially, let me just be a little bit, essentially the integral of k of the, so it's closely related, let's say this way, to the following, which means like integrating once, integrating in Q. And it obviously has integer coefficients by the integrality of the Catalan numbers, but if we integrate once, we still have integer coefficients. And so it wasn't obvious to us if this, so here I displayed an example of a component function of a vector valued logarithmic modular form in the previous definition, which has an integer q expansion. So the question is it related to modular forms, so quasi-modular forms? And indeed, Sudilin pointed out this formula to us, which is again a similar expression with the theta function and the theta operator. And so it belongs in some sense to the, so actually I have a definition here. It belongs to the congruence quasi-modular ring in the following sense. And now the open question. So that falls outside of our scope because we used a finite local monodromy around x equal to 0 in order for our analytic continuation step. So in this case, however, x equals to 0 has local monodromy z. It is for the logarithmic case. So the question is the following. Suppose we have this vector valued modular form, and we look at only one of its components. Suppose it has integer coefficient, integer Fourier expansion. And then, does it belong to the congruence quasi-modular ring, which is by definition the smallest ring that contains the weakly holomorphic modular forms, which means we require that they are holomorphic on the half plane, but they may have poles at cusps. On congruence subgroups of SL2Z, so we consider all congruence subgroups at once, and take the minimal ring closed, containing this, and closed under the derivative Ramanujan theta operator. So what we proved is the same, just crossing out logarithmic, and respectively, the conclusion is modular ring, instead of quasi-modular ring. So, but now, finally, the classical special case, which is obtained essentially when you have a monomial representation, or we have a classical just a modular form, scalar valued rather than vector valued is this. But I began with this because the questions that follow are related to infinite local monodromy at Z, necessarily by design, so to speak. So the classical theorem restated. I mean, the most interesting case, the core of the conjecture was now the theorem. If f has an integer Fourier expansion, that's the general sense of bounded denominators. And suppose it's modular for some finite index subgroup gamma, in this sense, then it is modular under congruence subgroup, or contrapositively, we usually have unbounded denominators if it's not congruence modular, but modular for some finite index subgroup. And now, my excuse for the slides, some of the pictures that I want to hope simplify the growth problem. We were, so before I get to the holonomy bounds proper, they involve a growth term. And in the proof of this theorem, we have to understand in some way the growth of the universal covering map of the complex plane punctured at all the nth roots of unity and based at 0. And we have what we have a overconvergence by the idea was that if we had a Zimmermann local monodromy at say local monodromy at x equal to 0, then and say we had certain singularities, so we normalize 0, 1 over 16 and infinity to be the singularities, then the new power series with f of x replaced by this will actually have an analytic pullback. So pulls back to a convergent power series on the whole unit disk under this universal covering, suitably normalized. So we take, of course, scaled an appropriate factor. So the pictures that, and then the overconvergence was from the fact that this the derivative or the conformal size of this surface is strictly greater than 16 to the 1 over n. So I give two examples. I think the only two that are parameterized by modular functions because of the accidents. So if you take remove the second roots of unity, then this is isomorphic to y of 2 by the function 2 lambda minus 1. I should say actually lambda avoids 0 and 1 if you take it on the upper half plane in the tau coordinate. And then the function 2 lambda minus 1 avoids plus and minus 1, take the K transformation, and then you can compute the derivative, and that gives you exactly, there's an explicit formula with the gamma function, this conformal radius. And similarly for n equal to 3, so we can see the numerics in these cases, there are strict inequalities that save our day in the algebraization method. So using these formulas, in general, there is no modular parameterizations, but the conformal radius is still a certain expression as a formula with the Euler-Gamma function. But for these three values of n, I have pictures of the, so to say, topography of these values. So of this function. So Fn is the universal covering map of C minus the nth roots of unity, and we are trying to show some level sets. So this will represent level sets of the map log absolute value Fn to power n, and then evaluated at the nth root of z. This is a holonomic function by symmetry of the nth roots of unity. So in this picture, all the colors represent different level sets. And so to say, there is a pole where the function grows very fast at q equal to -1. And the green level sets show the value 0, level set 0. So this is infinity, lambda equal to, this function equals infinity. Here, log of the function equals 0. And the warm colors, so to speak, where the function blows up, and we have to control the growth of the function. And finally, these dots that I have marked are three images of the points 1/9 and -1/8. So let us just track how the pictures change for the values n equal to 2, n equal to 3. And there is a certain convergence that to the limit case, and the limit case is is the lambda function. So in some sense, certainly locally uniformly on a fixed disk, smaller radius, we have as n tends to infinity, this function converges to log absolute value of the modular lambda function, but now as a function on the q disk. So in the q coordinate on the unit disk. So we had to estimate, to understand this convergence in some sense well enough to prove that a uniform upper bound on the Nevalida characteristic of the integral of log plus of this function, of these functions that we use on certain in the uniform measure of this circle on radius, and that had to be uniform in both, let's say, n and r. So we have a bound of this strength, which was proved with Nevalina theory. So now, however, we have, again, our examples will come from modular forms, but they will have denominators. So where these denominators will, they will emerge by iterated integration. So to say, I will maybe not try to get into Apery integrals and periods, but just displaying a page, this is essentially a version of Hecke's lemma from Berger's proof, irrationality proofs and modular forms. He was the one to discover this connection and reinterpret Apery's theorem, Apery's sequences in terms of modular forms. So we will see this in action when I explain the the rationality of the tuadic version of the zeta 5. But now this is where we are interested in these functions. So let me give an example of what we can prove. And the case k equal to 2 is a work in progress. So the idea is that, okay, firstly, we can show this for k equal to 1. This is a characterization of the logarithm function in arithmetic terms, sort of like the Borel-Quark rationality criteria. They characterize the rational function. This goes somehow, in some sense, a step further if we have those denominators. But it's a very restricted condition. So it says, if we have a formal function like I began, like I wrote down, a power series that has rational coefficients, and this integrality type, so it meant this is the LCM of the first 10 integers. We put some integer coefficients, sum it up, and then the logarithm is the main example. And then already if the singularities are 0, 1, and infinity, then yes, this function is a linear combination of the two functions 1 and log of 1 minus x. So they are the only linearly independent functions over the rational functions p of x. And this display is more general in that, so we can also assume that there are singularities that are close enough to 1 and close enough to infinity. Also we can allow singularities close enough to 0 as long as we assume the branch that we are taking, this particular power series, overconverges in the sense that it's holomorphic. This particular branch is holomorphic if we have singularities in this disk close to 0. So this is the precise statement in the sense I say that this is a compact subset omega that avoids 0, 1, and infinity. In practice, we just take exclude sufficiently small disk around these parameters. Furthermore, so observe that if we take the logarithm function, this li. So why was the bounded denominators conjecture proof particularly easy? That it is, for example, we have two levers that got us from to create new functions from old. So if first, if we have an integer formal function, like in that setting, then of course we can just raise it to powers, and we get new examples, and they will also be of the same singularities type, and still the same integrality type, and so this is why the algebraicity part was particularly easy. This representation row has finite image part, and there was also another level, which was, we assumed there was one counterexample, which is now a non-congruence modular form with integer coefficients, and then we can just replace it like this for some, for integer scale, and we get new examples. So, but now if we don't have this as integer coefficients, so let me just explain on the logarithm function. So if you take log 1 minus x, this and square it, there's a certain formula, but so it's we see that the denominator type gets worse, and so here this function will have an intermediate type of the form integers, multiples of x to the n, and then the denominators, the LCM of the first 10 integers times the LCM of the first n over 2 integers. Okay, so as a further step, we can say that if we have this denominator type, the solution space is a three-dimensional space with basis 1, log, and the square of log. And what we almost get to, but it's still a work in progress, try to finish. But it will be easy to say what improvement needs to be made. If we allow this denominator type, now like in Apery's sequences for zeta 2, for example, so we have then conjecturally there should be just a 4-dimensional vector space with this basis. There's also the dialog function. So this question is whether there's an arithmetic characterization of the dialog function similar to what we have for log.
So all of these are holomorphic in x less than half. Is that right?
Yes.
That's it.
Yes. So I mean the differential equation may have singularities, for example at 0, but you mean all of these examples?
So when you say the answer is you're still always imposing the condition holomorphic in x.
Yes. Oh, sorry, I meant to repeat in all of the following. Yes. So the same assumptions, just add one more. So all we do is relax the integrality type a little bit. Then I'm actually clueless whether, so there is a clear reason that we stop at sigma equal to 2, but so do we get new functions eventually for higher powers besides the polylogarithm limit?
Sorry, can you go back to the previous slide?
This one?
So you got, what are you saying about the dilogarithm? What exactly are you saying about the dilogarithm? I mean, there are these relations, I think you know them very well, Goncharov's. Are you saying anything about transcendence?
It is related, but so far I'm just...
I mean, you got work in progress, assume it works out.
So why? So I haven't answered why is that worth proving. And so far on this slide, it's just a question about functions. Can we find the arithmetic characterization of the dialog function? And now I'll try to explain why, how it is related. If we can answer that, we can answer a question in transcendence. So the goal, using the construction of Zagier, is so the irrationality of this value. So there is a question that is related to this.
So these are volumes of hyperbolic 3 manifolds, right?
This one, yes, this one is particularly, I believe, I believe this one is the largest.
Smallest volume. Anyway, yeah.
It's an interesting L value, although it's not, I believe it doesn't have a name. We call the Catalan constant, this one. But this, and this is of course the character. So this, I just write out the first few terms and it will immediately clear which character is meant. So this is 1 squared, minus 1 and 2 squared, and then alternating signs in this way. And you avoid the multiple of 3.
So your goal is to prove the analog of Apery here for these values, right?
That's right, yes. And we find that a lot of, even to prove the linear independence of this declared value with zeta of 2. So there is a construction due to Zagier, which reduces to proving that a certain G function does not exist. So it cannot, cannot have rational coefficients. And it would, and that in the end translates into a problem of this kind. So there is an integrality type, which is here, and the singularities are in some sense close to 0, 1, and infinity. So let me try to, maybe in 15 minutes, I can get to the construction. I was going to say, so this is one application that we aim for, and the other one that we have already proved by exactly the same. Sorry, I think, let me say. So products of 2 logarithms. So as far as I know, for the field of G functions, the range where we can prove irrationality of this product. Let me actually include also these four periods, the two individual logarithms, one and their product, and ask where can we prove for what values n and m can we prove linear independence over Q. And the classical theory, starting with Ziegel and Golochkin, and then, for example, the following statement is a very special case of Bombieri's paper on G functions. This is true and much more. For example, if n and m are sufficiently close, however, and then the meaning of sufficiently close is this. So to put the quantifiers, I say they exist where r is some constant less than 1. Now up to the value of this r, I believe this, I apologize if I'm wrong with this, but this should be the state of the art. So, for example, if you have n sufficiently big, I put an absolute implicit coefficient here. So, for example, if you have m equal to n plus 1 or m equal to n plus 100, and you take n to be large enough, then yes, these are linear independent over Q or over any number field of a fixed degree. Have to change the meaning of sufficiently large. So because this is a theory for algebraic relations of special values of G functions at arithmetically small arguments like 1 over n, or like or like square root 2 minus 1 to the power n, where n is very large. Now we have two arguments, m and n, and it has to be quantified. So the application, I'll just sketch in one word, applying, let's say, Bombieri's paper on G functions with a single variable G functions, which would be like something like log 1 minus x, and then you have times log of 1 minus x on 1 plus k times x, where we write n equal to n plus k. And okay, this for a fixed k is a G function, but it has certain new singularities that depend on k. And so the height of the G operator that I'm related involves k. And then we have to, making everything quantitative, we have to say how small k is with respect to n. It comes down to this, what I wrote on the other board. And in comparison, we have a very restricted result, but it is in this range. M and n are sufficiently close in the following sense. So epsilon naught is a certain absolute positive constant instead of this. And the reason that this works, and there is also Diophantine approximation. Version, which should look in this form. What makes, so now going back to this lambda function and its external property. So let me somehow say what makes this integrality type special as opposed to other higher powers, is that, so this turned out the theorem of Karath-Theodori, as we later found out, what we found about the lambda function. So lambda of Q, observe that it maps now in the cusp filling coordinate of the Q disk. So the cusp I infinity. So Q equal to e to the pi I tau. And then the lambda function is a certain holomorphic function on the unit Q disk, avoiding 1, and with fiber a point over 0. Therefore, so of course it's not injective, it's not univalent. But among all the functions with these two properties, so these properties, in some sense, good enough for instead of univalence. So among all these functions, the derivative 16, or the conformal size of this map, so to say, this is the derivative at the origin, is maximal. And the point is that 16 is bigger than e squared. So here is at this point I can state the what we are calling the holonomy bound. So we have there's an integrality type. In general, we can have several powers and b. And let us also consider for each place v of q an analytic mapping of the unit disk, v-adic analytic mapping of the unit disk. By analytic, I just mean a convergent power series that maps 0 to 0, which is, let's say, the identity for almost all places v. We can be loose about the multiple of the identity, provided this condition holds on the derivatives, and we call this datum x. So we're trying to solve a certain Diophantine problem in terms of the, given this datum. We are interested in the QX linear span of all the formal power series for our purposes, f of x with rational coefficients, which, so we have to match an integrality type against an analytic continuation property. Integrality type, well, there are integer coefficients an, for which the function has this form. And we demand that the pullback of f and all of our mappings phi converge on the unit v-adic disk. So normalized so that the radius is 1. I mean, we look at phi is defined on the unit disk. And we interpret for the starting point the algebristic criterion of Andre in the following qualitative form. So this is the loose version, less precise version of the what we are calling the holonomy bound. So we have a bunch of this notation. Sometimes I think it's fairly standard in G functions theory. We denote tau to be the total power. Okay, this quantity. So this is the part of the height of the power series that comes from genuinely from the denominators, not from p-adic convergence radii. So these LCMs that we use. And the arithmetic degree will be the sum over all places of the logarithms of these conformal sizes. So there are, and then we, okay, so the basic fact is that given such a datum, and we then look for the solution space, this solution space is either a finite dimensional vector space over the rational functions, in which case it consists of holonomic functions a priori. And that is when the arithmetic degree, that means the maps are sufficiently big in the conformal sense. So the analyticity wins over the denominators type. So this strict inequality holds.
So what does it mean, holonomic functions?
Sorry, I should have said, yes, it means satisfy a linear differential equation with coefficients in Q of x.
Okay.
Yeah, so, and then the reason why, so finite dimensionality implies holonomic is because the solution space by the chain rule is closed under derivative, under ddx. And there is no structure. Let me just say, like infinite dimensional space or even continuum, if this inequality was not satisfied. So our whole game,
even in the borderline case.
Yeah. In this case, it's even then. Yes, this is like in the Robinson's paper on irrationality criteria, he takes the effort to prove, like there are, if in the borderline case, for any domain in the projective line, there are infinitely many non-rational functions. Like, so, however, that's actually a great point that in the borderline case, okay, so this is what I tried to say about this example with the lambda function. And so now these properties make it automatic that if we have f is holonomic, so it satisfies a linear differential equation on I mean p1 minus 0, 1 and infinity. So it means that L has no singularities other than those three. And then for any such function f, these properties alone ensure that the pullback on the lambda is holomorphic, convergent power series on the Q disk. So our original problem with singularities and denominator types fits into this formalism, and then this example has conformal size log 16, so that wins over 2, and therefore we have a shot at attacking at least this case with erased, let's say, the dilogarithm that we try to characterize in an arithmetic way. Okay, so the basic problem is, I think I stated the expected solutions. And now this was the point about the borderline case. I will not ask a precise question, but if we have the borderline, the arithmetic degree is exactly equal to the tau, then there will be many formal solutions, but they will not have any holonomic structure if we restrict to a priori holonomic ones or a priori algebraic ones. So this is the starting point for this setup with take a modular form with integer quick expansion, then write it out in lambda over 16, you get a certain boundary case a priori. So yes, are they somehow related to modular forms, or can we cook up other holonomic examples in the boundary case? Not a precise question. So I think I should end with displaying the main quantitative result, including with Diophantine approximation. So very quickly, I'll just say now more generally we can have do I have? Oh yes, sorry, we started at past 10. Okay, so I have time to state it. Give such a datum x. For simplicity, I'll only assume that only the Archimedean phi, the Archimedean map is non-trivial, and all the others for the primes, I will take the identity. Then I'll take m tuple of formal power series with real coefficients. Maybe these coefficients involve zeta 3 or zeta 5 periods, and that we try to approximate by rational sequence. And suppose that the GI have an analytic pullback on the disk. Unlike in the Diophantine approximation, suppose that there is an exponent kappa and a radius rho. I just hope this is not too technical, but if it is, for the following, you can think of kappa equal to infinity. So in that case, okay, we'll see. It simplifies. So then suppose we have a sequence of positive integers q that go to infinity, and for each such q, we are given now a rational coefficients power series. We'll think of the GIs as the target of the Diophantine approximation problem, and the Fi are like the rational approximants, but that is now on the level of formal functions. Now q is, so we suppose that q times Fi has the integrality requirement for this, what I call the Delic template X. So this denominator integrality type, if we clear denominator of q, we have that. And I'll take rho to be a convergence radius common to all of these Fi put back by phi. And now I'll tell you how to simplify this for the qualitative version with kappa equal to infinity. The final bit of notation is we take also the least convergence radius of one of these Fi's. And then we want the approximation problem will be that coefficient-wise, these two power series, Fi minus Gi, are close within this. So that simply means that uniformly, with implied coefficient that does not depend on Q and N, all the coefficients, say the N coefficient of Fi minus Gi is big O of Q to the minus kappa times R to the minus F. Now, if kappa equals infinity, that just means that F is equal to G. So there are only one piece of data. In that case, we just have those rational coefficient form of functions F. And there is no Diophantine approximation data. Then the quantitative version of this of the previous theorem is the following. So suppose we have these targets Gi, and then we have a sequence of levels, and for each Q we have those approximant in the coefficient-wise sense. And we suppose that this analytic mapping phi is large enough in the following sense. It has conformal size strictly bigger. Now there's the tau of the template. There is this approximation exponent kappa that I had, and rho. And then we have the following upper bound on M, which is assuming these functions are linearly independent over Q of X. So this is the dimension bound. So what does that tell us for the qualitative case without Diophantine approximations? We'll just take the case alpha equal to infinity. So it means that the dimension over the rational functions of the sum of all solutions by solutions in Q of X that have already analytic cubes. This is smaller than or equal to that display. So with kappa equal to 0, this is simplified. And for instance, for example, just to state one case of this, I'll choose lambda. Lambda is an arbitrary integer parameter. We can just take it to be the supremum of this phi, in which case the integral just vanishes. This has a lot plus. And so an example of what we call the holonomy bound, which essentially already goes to Andrei's book on G functions, is by the supremum of log. So this is what we have, that's the growth term, and divided by formal size. In previous discussions, and for what is relevant to the to unbounded denominators paper, we had tau equal to 0 before. And now our game is to so I obviously wrote more things than I can cover, but there is a more conceptual refinement of original tau equal to 0 dimension estimate, which was proved by Bost and Charles, and it includes in the previous display, if we have kappa equal to infinity and tau equal to 0, it unifies both of these cases by a double integral. Okay, and then I have the proof outlined by Bost-Slopes method, but I think let me conclude with showing one application finally to this one, to irrationality. So everything is in the following spirit. I hope this will be some illustration of the game that we're trying to play against those holonomic bounds. So of course, for the Archimedean place, the classical zeta 5 value is this infinite convergent sum. So, and of course, the periodic meaning of that is not so direct, but we have to, we take the unique periodic number, is constant, for which this Q series is a periodic modular form. And that would mean following series, a limit of the expansion of classical modular forms, I mean periodic limit, or it could mean this rigid analytic section over the ordinary locus, or it could mean essentially going back to Kummer, this Bernoulli congruences, this limit. That means we've taken out the p factor or the factor at the prime 2, and that's as concrete. I'm not sure, I hope I computed these digits correctly, but so complete periodic number. So and the irrationality theorem means these are not eventually periodic. So how do we reduce to the holonomic bounds? So we have I just outlined Calegari's periodic analog of Apery's formulas. So this is just the algebraic usual Eisenstein series of a positive weight 2k, except with removing out the p factor, and then for negative weights we can have the following, which is now periodic modular form, but it is an overconvergent eigenform for the U operator and this level gamma 0 of p. So they have opposite weights, and we can now observe that it's like these integrals that introduce denominators. So here, okay, this is essentially it has integral coefficients, and this one has. Now we take the divisors of n, and we take powers of 2k plus first powers, and when we put the LCM of the first n terms, we get those denominator types exactly. In this case, exactly this LCM of the first n integers. Well, it's q to the n, and then to this power 2k plus 1. So we will choose k equal to 2, and then tau is equal to 5. So, and then the only transcendental or conjecturally transcendental piece in this formula is this I12 period. So say only the constant term, and everything else has rational coefficients. So we just multiply those two functions, h, and we get a certain formal function which should not have rational coefficients. But you see that it involves both this and that Eisenstein series, so that they get mixed up with. So if this constant were rational, we would get a rational coefficient. We would get a g function. And now we're trying to show that such a g function cannot exist using these arithmetic algebraization methods. Now, similarly to lambda, we take this Hauptmodul of x0 of 2. Now, the rings z of x and z of q are equal. So we are in this setting. I can replace q by x and still have this denominator type. And by theorem of Buzzard, this function h has a very huge twadic radius because it will have to, I mean, this eigenform e minus 2k has to extend through the supersingular annulus, which is this. And so the twadic radius, the upshot is that h of x is some formal function with twadic radius as big as 2 to the 12. And then if this, under this absurd assumption that we have a rational constant here, h would be a g function. It has q coefficients, tau will be 2k plus 1, type is this, periodic convergence radius is 1, and finally, so I end with just showing the choice that conflicts our dimension estimate. we choose the, so this is similarly a topographical picture with certain level sets of the half modular x of q. And again, these kind of warm colors show the part where the function is very large. So this disk of diameter -1/7 is the supremum of the function is very small, and we have one of the bounds I had written out amounts to this sort. So we say that there are at most 5 solutions, at most 5 sub G functions, but actually if H were a G function, if it had rational coefficient, then taking its derivatives would give us 6 linearly independent functions. It's easy to see that H is a priori holonomic, but if holonomy rank exactly equal to 6, that's a general fact, just by, say, computing the monotromy, and we get into contradiction in this indirect way. So unfortunately here, taking derivatives is about the only way to get new functions. Okay, so apologize for writing apparently many more things that I could say. Thank you very much for your attention. I'll stop here. Are there any questions?
Yeah, hi, great talk. Can you actually state this last thing? What are you proving? Zeta of 3, two-adic zeta of 3 is irrational, or are you proving something about odd zetas or Rivuel ball type theorem? What are you proving?
What is zeta 5 is irrational.
Sorry, zeta 5, but you don't get zeta 7, for example.
Not zeta 7, although it's potentially within. Okay, we couldn't get to that, at least not yet. Okay, it's potentially within the scope of the method, so to say. It still recognizes this function h as holonomic in this arithmetic way, but the numerics are not good enough to get a similar proof. I could say that zeta 3, yeah, this one was done by Calegari in his original paper. So we build on his method for this.
So your new one is zeta 5, and I guess you have an analog of Rivuel. Well, I guess they know that already, that the dimension grows, yeah. So that's much easier, I guess, yeah.
Yes, we are trying to get at exact linear independence or irrationality for not saying infinitely many are irrational, but.
Okay.
Yes.
And how about the dilogarithm? Any exact statement that you have at this point?
So in that case, I should say there is. I mentioned these 3 periods. So let me just say that if there is so again, an absurd assumption that okay, suppose there is a collinear dependence, and that similarly induces okay, so we're trying to get a contradiction in a similar way, and that due to Xavier. So he tried to computationally discover.
Is it zeta of 2 there?
Zeta of 2, right. So just he took Apery's versions for zeta of 2 and found other examples that included also realized this, say, as an Apery limit. So that's based on gamma 0.6. But suppose there is a linear dependence of this, then we can write down a function h of x, which should not exist, which is of this integrality type I wrote, x to the n, plus 1n squared, with some integer coefficients an, and which has now singularities on 0, 1/9, that's special, 1 and infinity. However, it is over-convergent at 1/9 and obviously at 0. So in some sense, it's close to this problem that I tried to describe at the beginning with the dilogarithm function. So dilog is similar. It has singularities of 0, 1, and infinity. Now, if we had this linear dependence, we would get other solutions, other similar functions. So there's h of x, there's h prime of x, there's h of this substitution x on x minus 1 and its derivative. So these 4 functions are linearly independent, and they are linearly independent also from the 4 true examples we had. 1 log, this is log of 1 minus x, log squared, and dialog. So these 8 functions are all solutions to one of the problems I have, which is this denominator type, these singularities, and we just need to derive a contradiction ultimately and get this linear independence, or also independence measures. All we need to do is prove a holonomy bound by less than 8. And currently we just have at most 8 such.
Okay, fantastic.
But yes, so I try to.
Okay, thanks. Yeah, you'll get there.
I believe so. So I couldn't get to the. We will see.
Thank you.
Where does this holonomy terminology come from?
So does it from? I mean, holonomic sequences and linear differential equations, is that just the same name? I mean, 2 names for the same. I'm not even.
Yeah, I think of holonomy as some kind of differential geometry word.
Is it? Yes, but this is about sequences. So maybe these words are interchangeably used as definite. So suppose AN sequence of complex numbers which satisfy a linear recursion with polynomial coefficients. So that's defined as holonomic, I guess. And that's where I just take the term. And that's, of course, just an expression. It's equivalent to the differential equation. Yes, I should know better. But no, it is related to holonomy in the sense that we have these. I mean, we take a loop around one of the singularities, and we see one of the periods emerge as coefficients.
So did you actually prove it, or are you just using the terminology?
Just to use so holonomic for me means just exists L, a linear differential operator, with polynomial coefficients. So let me say just over the rational field with L equal to 0. So just that.
There are no more questions. Let's thank Vesselin again.